In 1974, I published a paper in Nature that should have been impossible, proving that black holes actually glow, radiate energy, have a temperature, and given enough time, evaporate completely and die. These objects were supposed to be the ultimate cosmic prisons, so dense that nothing, not even light, could escape them, and yet my calculations showed they were slowly bleeding energy into the universe. This single discovery created a paradox that physicists at Cambridge, Princeton, Caltech, and institutions around the world are still fighting about 50 years later. My colleague Roger Penrose won the Nobel Prize in Physics in 2020 for work we began together on these objects, and in 2019, the Event Horizon Telescope captured the first photograph of a black hole's shadow in the galaxy M87, giving us visual confirmation of what had been pure theory for a century. Everything you think you know about black holes is incomplete, and I want to show you what's really happening inside them, along with why the answer threatens the foundations of physics itself. Most people picture a black hole as a great dark sphere floating in space, pulling in everything around it like water circling a drain. John Wheeler, the Princeton physicist who gave these objects their name in 1967, chose the term precisely because it captured this image of absolute finality, where what goes in stays in, and the whole grows larger. That picture has several problems, and they're the kind that keep theoretical physicists awake at night. Consider a thought experiment where you're watching an unfortunate astronaut falling toward a black hole. You would see something peculiar as they approach what we call the event horizon, because their movements would appear to slow down as if they were moving through treacle. They would grow redder and dimmer, and just as they reach the event horizon itself, they would seem to freeze entirely, stretched across the boundary like a photograph, growing ever fainter until they faded from view completely. Here's the thing that should make you uncomfortable, and it's that from the astronaut's perspective, nothing unusual happens at all. They simply fall through the event horizon without noticing any particular boundary, passing from outside to inside. And if they weren't already aware of their predicament, they might not even know they'd crossed into territory from which there is no return. Both of these accounts are true, because the answer lies in the nature of time itself. Near a black hole, time runs slower. And this isn't a trick or an illusion, but something as real as the ticking of your watch. Einstein showed us that time is not absolute, and that it flows at different rates depending on how strong the gravitational field is where you're sitting. For the distant observer, the astronaut's clock runs slower and slower as they approach the event horizon, and at the horizon itself, time comes to a complete stop relative to the outside universe. An infinite amount of external time would pass while the astronaut crosses that boundary, which means that, from out here, they never quite make it in. Your grandmother on Earth ages faster than you in orbit, and both of you age infinitely faster than that astronaut frozen at the horizon's edge. The astronaut experiences nothing unusual about their own time, with their heart beating normally and their thoughts proceeding at their usual pace, all while falling unaware that the universe outside is aging faster than they can imagine. This is your first glimpse into why black holes are far stranger than the simple picture suggests, because time and space themselves become strange, and what seems permanent from one perspective is temporary from another. The story of how we came to understand black holes is itself a tale of ideas too strange to be believed at first. A Cambridge clergyman named John Michell wondered in 1783 what would happen if a star were so massive that light itself couldn't escape its gravitational pull, and it was an inspired thought that was soon forgotten because the mathematics didn't exist to make sense of it. Einstein changed everything with his general theory of relativity, and in 1916, barely a month after Einstein published his field equations, a German physicist named Karl Schwarzschild solved them exactly for a spherically symmetric mass. Schwarzschild was doing this while serving on the Russian front in World War I, performing calculations between artillery barrages, and what he found was disturbing because there was a radius at which space and time themselves became infinitely curved, creating a point of no return. The scientific community largely ignored this result because Einstein himself thought it was merely a mathematical curiosity that couldn't exist in nature. Surely, they reasoned, no real star could collapse to such a state, and they were wrong. Subramanian Chandrasekhar calculated in the 1930s what happens when a star runs out of fuel, showing that for stars above about 1.4 times the mass of our sun, there's nothing that can prevent the ultimate gravitational collapse. The star continues shrinking with its matter crushing together until it forms something with such enormous density that escape becomes impossible even for light. When Chandrasekhar presented this idea at a meeting of the Royal Astronomical Society, the great astronomer Arthur Eddington stood up and essentially told him it was absurd, insisting that the universe must have some mechanism to prevent such an obscene outcome. Chandrasekhar was devastated, and he later received the Nobel Prize in Physics for this work in 1983, but only after decades of having his ideas dismissed. This pattern would repeat because black holes are so contrary to our intuitions that the brightest minds consistently underestimated them, and I would make this mistake myself. One could well say of the event horizon what the poet Dante said of the entrance to hell, that all hope should be abandoned by those who enter. Let me be precise about what the event horizon actually is, because it's commonly misunderstood, and it is not a physical surface. You cannot touch it or see it because it is simply a boundary in space-time, the point at which the escape velocity equals the speed of light. Cross it, and you are committed, with no engine powerful enough, and no force in the universe strong enough to carry you back out. Inside the event horizon, all possible futures lead toward the center. And I don't mean just the likely futures or the probable ones, but all of them. The singularity at the center of a black hole lies in your future as surely as next Tuesday lies in yours right now. And trying to escape would be like trying to travel backward in time. Now imagine our unfortunate astronaut falling in and what happens to them. As they descend, they begin to feel something uncomfortable because the gravitational pull on their feet is stronger than the pull on their head since their feet are closer to the singularity. This difference in gravitational force, which we call tidal force, begins to stretch them, and their body elongates while the sensation becomes painful, then agonizing, and finally unsurvivable. They are stretched like spaghetti. I didn't coin that phrase, but I did help popularize it, and spaghettification sounds almost whimsical even though the reality is anything but. The astronaut is pulled into a long, thin stream of particles, stretched to impossible lengths as they approach the singularity. For a small black hole formed by a collapsing star, this happens well before you reach the event horizon, and the tidal forces would tear you apart millions of kilometers from the boundary itself. Here's something curious about truly massive black holes, the kind we find at the centers of galaxies like Sagittarius A star, at the heart of our own Milky Way, containing millions or billions of solar masses. The event horizon is so far from the singularity that the tidal forces there are quite gentle, and an astronaut could cross the event horizon of a supermassive black hole and feel nothing unusual at all. They would have time to contemplate their situation, to observe their surroundings, perhaps even to conduct experiments, and they would only be spaghettified later as they approach the central singularity. You could cross the point of no return, the boundary from which nothing can escape, and not even notice. No sign, no sensation, no fanfare, just an ordinary moment that seals your fate utterly and completely. Now let me tell you about my discovery, the one that changed everything, and let me tell you how I nearly missed it by arguing against my own student. My student Jacob Bekenstein noticed something peculiar about black holes before I made my breakthrough, observing that they behave a lot like thermodynamic systems, like hot objects that have temperature and entropy. Entropy is a measure of disorder, or more precisely, of how many different microscopic arrangements are consistent with the same macroscopic appearance, and a cup of hot water has high entropy because its molecules could be arranged in countless different ways while still looking like the same cup of water. Bekenstein noticed that the area of a black hole's event horizon behaves exactly like entropy because when anything falls into a black hole, the event horizon grows and never shrinks. This is remarkably similar to the second law of thermodynamics, which says that entropy always increases. I initially resisted this idea and even argued against Bekenstein publicly, and my objection was simple. If a black hole has entropy, it must have temperature, and if it has temperature, it must radiate energy, but nothing can escape from a black hole. So I thought I had found a fatal flaw in Bekenstein's reasoning. What I found instead, when I tried to prove him mistaken, changed everything. In the early 1970s, I was thinking about what happens near the event horizon when you take quantum mechanics into account, and classical physics, the physics of Einstein, treats the event horizon as an absolute boundary. Quantum mechanics, governed by Werner Heisenberg's uncertainty principle, tells us that empty space is never truly empty. This should break your brain a little, so let me explain it carefully. According to quantum theory, the vacuum of space is seething with activity, and pairs of particles are constantly appearing out of nothing, existing for the briefest moment, and then annihilating each other. One particle has positive energy while the other has negative energy, and when they meet, they cancel out completely. Think of it as the universe running a bank with impossible rules, where loans must be repaid instantly, principal plus interest, no exceptions. These are called virtual particles, and they're constantly flickering in and out of existence all around you right now. Near a black hole, something extraordinary can happen to these particle pairs. Imagine a pair of virtual particles appearing just outside the event horizon, and normally they would exist for an instant and then annihilate. At a black hole's edge, one particle can fall across the event horizon while the other escapes, which means they can no longer reunite. The escaping particle becomes real, with permanent existence, and the one that fell in had negative energy, which reduces the mass of the black hole. The escaping particle effectively steals energy from the black hole to pay what the universe is owed, and the universe's accounting remains balanced while the black hole's doesn't. From far away, you see radiation streaming away from the black hole, and the black hole appears to be glowing. Black holes ain't so black. This radiation now carries my name, and it's thermal radiation like the glow from a hot coal, with its temperature depending inversely on the mass of the black hole. The smaller the black hole, the hotter it glows, and a black hole with the mass of our sun would have a temperature barely above absolute zero, far too faint to detect. A black hole the mass of a mountain would be blazing hot, glowing white with radiation. Here's the most remarkable part of all this. Because this radiation carries energy away from the black hole loses mass and shrinks, and as it shrinks, it gets hotter and radiates faster, so it shrinks even more. This is a runaway process, and given enough time, the black hole will evaporate completely. Let me say that again because it's extraordinary. Black holes are not eternal, and they have a lifespan. A black hole, the mass of the sun, would take about 10 to the power of 67 years to evaporate, which is unimaginably longer than the current age of the universe, longer than all the stars will shine, longer than nearly anything else will exist. Even the greatest black holes will fade eventually, and the permanent prison has a release date that just takes a very, very long time. The LIGO Observatory detected gravitational waves in 2015 from two black holes merging, which created ripples in space-time itself, and confirmed that these objects behave exactly as Einstein and I predicted. The universe keeps providing evidence. I was so confident in my radiation result that I made a bet about it, and in 1974, my colleague Kip Thorne at Caltech and I wagered on whether Cygnus X1, a powerful X-ray source in our galaxy, actually contains a black hole. I bet against it. This might seem odd since I bet against the very objects I spent my life studying, but here's my reasoning, and it reveals something about how scientists actually think. I had done a lot of work on black holes, and if it turned out they didn't exist, all that work would be wasted, but at least I would have the consolation of winning my bet. It was a form of insurance. The evidence became overwhelming, and I conceded, which meant Kip won a subscription to a magazine called Penthouse. My wife at the time was not entirely pleased. Betting and being proved wrong is part of science, And what matters is following the evidence, even when it contradicts your expectations. The evidence for black holes became undeniable. Now we come to the deepest puzzle of all, the one that occupied physicists for decades, the one I wrestled with until the end of my life, and the one I was wrong about again. When matter falls into a black hole, it carries information, and a book contains information in the arrangement of its atoms and in the patterns of ink on paper. A person contains information in the structure of their brain, in their memories and thoughts, and the unique arrangement of every molecule in their body. According to my original calculation, that information is lost forever because the radiation that escapes from a black hole is thermal, which means it's random noise like the static on an untuned television. It carries no information about what fell in, and a black hole formed from a collapsed star looks identical to one formed from a pile of encyclopedias. When the black hole evaporates, all trace of what created it has vanished. Consider what this means for everything else in the universe. Every hard drive that fails and every library that burns, we believe the information is merely scattered and not erased, and given enough time and computing power, it could theoretically be reconstructed. The laws of physics are supposed to be reversible, but black holes, according to my calculation, threaten to be different. They threaten to be the universe's true delete key, permanent, irreversible, and final. One of the fundamental principles of quantum mechanics is that information can never be truly destroyed, and you can scramble it and transform it beyond recognition, but in principle, you could always reverse the process and recover what was lost. If black holes destroy information, this principle is violated, and the past becomes fundamentally unknowable, not just difficult to reconstruct, but impossible, even in principle. I argued for many years that information was indeed lost, and this brought me into conflict with many of my colleagues, particularly Leonard Susskind at Stanford, and those working on string theory. Kip Thorne and I bet against John Preskill of Caltech in 1997 that information was truly destroyed, and we made formal wagers and had heated debates at conferences around the world. I changed my mind eventually, not easily, and not without resistance, but the arguments against information loss became compelling. I conceded the bet to Preskill at a conference in Dublin in 2004, and I gave him a baseball encyclopedia, a book from which information can be retrieved at will. The resolution may involve the idea that information is somehow encoded on the event horizon itself, imprinted on the boundary like words on a page, and we call this the holographic principle. It's as if the black hole runs a compression algorithm so powerful that three-dimensional reality can be encoded on a two-dimensional surface, like storing a sculpture's complete information in its photograph's pixels, except perfectly with no loss. When the black hole evaporates, this information escapes in subtle correlations in the radiation, and the process is so scrambled and so complex that the information appears to be lost, but in principle it's still there. The three-dimensional world we experience might itself be a kind of projection, a shadow of information encoded on some distant surface. Black holes have taught us that space itself may be an illusion. I must be honest with you because we don't actually know what happens at the singularity since our equations break down there. The curvature of space-time becomes infinite, and our theories produce nonsense answers with infinities where there should be finite numbers. This is a signpost because whenever physics produces infinity, it's telling us that we've pushed a theory beyond its domain of validity. General relativity, Einstein's masterwork, stops making sense at the singularity, and to understand what truly happens there, we need a theory that combines general relativity with quantum mechanics, a theory of quantum gravity. We don't have such a theory yet, and we have hints and pieces and promising ideas, but no complete picture. The singularity inside a black hole is where the known laws of physics end, and it's the edge of the map where ancient cartographers would write that here be dragons. Perhaps the singularity is truly the end, a place where existence itself terminates, or perhaps something else happens that our current theories cannot describe. Some physicists speculate that the singularity might be a gateway to another region of space-time, perhaps even another universe, and this is the idea behind so-called baby universes, that black holes might give birth to new cosmic realms causally disconnected from our own. I held the Lucasian Professorship of Mathematics at Cambridge, the same chair once held by Isaac Newton, and I thought about these possibilities for years. They're speculative, but they're not impossible, and the universe may be far more complex than a single connected space-time. From your perspective, if you fall into a black hole, you cross the event horizon without drama, and if the black hole is large enough, you might not even notice. Inside, you continue falling toward the singularity, and space and time behave strangely there, because what was once the center becomes your inevitable future, as inescapable as tomorrow. As you approach the singularity, tidal forces grow and your body stretches, and the atoms that compose you are pulled apart, then the nuclei, then the quarks themselves. At the singularity, space and time as we understand them simply end, and there is no after the singularity, no next moment, no further destination. Here's what we've learned though, which is that in some sense, you also remain encoded on the event horizon. The information that defines you, that makes you who you are, is smeared across the boundary as you fall through, and when the black hole eventually evaporates in the unimaginably distant future, this information escapes back into the universe. Whether this constitutes survival in any meaningful sense, I cannot say, and the information is so scrambled and so transformed that it would be unrecognizable. It persists, though, and the universe keeps its records. I've often been asked whether falling into a black hole would be a good death, and there's something appealing about it, to see what's inside, to witness the singularity, to experience conditions that no human has ever encountered. I've also said this, though, that if you feel you are in a black hole, you shouldn't give up because there is a way out. The radiation that I discovered means that escape is possible, not for you as a coherent person, perhaps, but for the information that constitutes you. The black hole will eventually return what it has taken. That's what black holes really teach us. that the universe is stranger than we imagined, and stranger than we can imagine. The permanent is temporary. The inescapable allows escape, and what appears to be destroyed persists in hidden forms. Every time you look at the night sky, you're seeing a universe shaped by black holes, because they sit at the centers of galaxies, and form from dying stars, and warp the fabric of space and time itself. Slowly and imperceptibly, they are evaporating, and the radiation is too faint to detect with our current instruments, but it's there. The longest prisoners eventually go free. I was wrong about Bekenstein's entropy, and I was wrong about information being destroyed. Being wrong and admitting it, and following the evidence to new understanding, that's what science actually is, and that's what understanding the universe is really about. It's not about finding comfortable answers, but learning to accept answers that challenge everything we thought we knew. Somewhere out there, in the radiation streaming from ancient black holes, the scrambled information of everything that ever fell in is making its way back to us. The universe forgets nothing, and even when we can't read the message, it remembers.